Section 2.4 is going to cover finite and infinite sets. So let's take a look at some definitions and then we're going to look at some examples. On this slide, we're going to look at one-to-one correspondence and finite sets. And I want to use this introduce this by using a ministry example. In our church, we recently participated in a project called The Gospel to Everyone. You might be familiar with this. In our state, we had a project where the state office had enough of the Jesus movie DVDs and some different gospel tracts to give to every household in the state. And then they partnered with all of the associations throughout the state, and we then, local churches, divided up the different households, and we were given an area and a map of 5,000, roughly 5,000 homes within a couple mile radius of our church, and we were tasked with delivering these packets of materials, one to every household. And so we had to put together these packets. The state gave us all of these materials for free, and we were able to include some materials from our church. We were able to put in some stuff giving information about our church, and we put in some Bibles and some flyers about VBS, different things like that. And then we had to divide up into teams and set out to go door to door handing out these gospel to everyone packets. So it's a really neat project. So as you can imagine, it was set up that we had one packet per household. So in this particular set, that was a one-to-one correspondence. Every household that was on our map, that was the set A, received a bag, which was set B, with the Jesus movie, the gospel presentation that was in that set. So that is called a one-to-one correspondence. We knew exactly how many households there were. We prepared the same exact number of sets of bags, and we matched them one for one. That's what a one-to-one correspondence is. This is also known as a finite set. So a finite set just means that it can be counted. We could look it up on a map and we could count them. So finite means that we can put a number to it. All right, so that's one-to-one correspondence and finite sets. Now, then you can compare that with an infinite set. Now, if you consider, what if I were to say that I wanted a set that contained all of the grains of sand on the seashore? That is an infinite set because it cannot be counted. You know, if you started counting the number of grains of sand, you would start counting 1, 2, 3, 4, 5, so on. But it cannot be counted. It goes on and on and on forever. Well, it turns out that all of your number systems, the number systems that we learned about in a previous section, your natural numbers, your integers, your real numbers, your whole numbers, all of those are considered to be infinite sets. So this funny looking symbol right here is called aleph naught or aleph null. So sometimes you'll see it written as and called aleph naught or aleph null. It was created in the 18th century by George Cantor, and it's basically just a way for us to depict an infinite set. And the only reason I kind of tell you about this is because you're going to see this weird looking symbol and this terminology in your homework. So anytime you are asked to count an infinite set, well, it can't be counted except that whenever you have to talk about an infinite set, you can talk about it. And in your homework, you're just going to write, I think they want you to write Aleph null without the dash. They'll tell you to write it in all caps, Aleph null, and it'll tell you that specifically. So anytime if you're asked to count, to give the count or cardinality of a set, and the answer is that it's an infinite set, then that's going to be your answer, this Aleph null. And the reason is because that's how you would describe an infinite set. The last definition I want to talk about is the Cartesian product. So a Cartesian product of sets A and B is the set of all ordered pairs x and y, where x is an element of A and y is an element of B. So if you go back to the very beginning, a couple of slides back, we actually talked about the Gospel to Everyone project. And we talked about sets A and B where we had the set of households. That was set A. So we had set A were the households and set B were the bags. So we would have A would be all of the different households. So we could take households in each neighborhood here. And then B would be like the bags. So we would have the bags out of each box or whatever. And so we would have each bag that would go to each household. So it would be an ordered pair. So X is an element of A and Y is an element of B. And you'll see this will make a little bit more sense here in our next example. Then you have the cardinality of a Cartesian product. Remember, again, the cardinality is just the count or the number of elements in the Cartesian product. So the number of elements in that cross product is going to be the number of elements in A times the number of elements in B. Okay, so it's a direct multiplication. And so you're going to see that in our next example, and all of this will make a lot more sense.
And so let's take a look at and go ahead and define that so we know that what we're looking at. Suppose you have the set A, which has 7, 8, and 9. And suppose you have the set B, which contains the lowercase letters A and B. We want to find what is the cross product or the Cartesian product of A cross B. And that's how I usually say that, A crossed with B. Now, I like to set this up in a table format. Whatever is my first set, I will actually put here along this vertical part of my table, and then whatever is set B, I put along this horizontal top part. And then I'm going to do all of my products in here. And so let's see how they look. You're going to basically pair the 7 with the A, and that's going to go in this first block. And so, so you'll see I've done the product of 7 and A, and they will be written as an ordered pair. And then you have 7 crossed with B, that will be the ordered pair 7B, and then 8A, 8B, 9A, and 9B. Now, when you write these out, this just helps me to keep everything organized, because when you try to write it out without using this table, sometimes one gets lost. So I just like to use the table. But when you write it out, you'll want to write them all out, and notice that you have your ordered pair, and each ordered pair is separated by a comma. So when you do your homework, you need to make sure that this is how you write this set. So with the brackets, and then separated by commas. Okay. So now let's look at the same exact set. Oh, well, before we do that, let's look at the cardinality of the set A crossed with B. And it turns out by definition that if you're looking at the cardinality of that set, you're going to take the cardinality of A and multiply it times the cardinality of B, and that's how many sets should be in your crossed set. So in other words, I have three elements in A, I have two elements in B. So 3 times 2 equals 6. So A crossed with B should have 6 elements. 1, 2, 3, 4, 5, and 6. Okay. Now let's take the same set and instead let's find B crossed with A. And you're going to see that this is actually a different set. You would think it'd be the same, but it's not. So let's line up our table. And again, take the first set here and I line it up on this vertical axis. I take my second set, I line it up on the horizontal axis, and then you do your cross products. So we're going to have the ordered pair A7, A8, A9, and then B7, B8, and B9. Now you can write all of those out in B crossed with A. Again, make sure that you separate your ordered pairs with a comma. And then if you look at your cardinality, it turns out that the cardinality is going to be the same. So whether we did A crossed with B or B crossed with A, we still get that there's 6 elements in the set. Okay, now let's continue talking about cardinality, but this time I want us to think about the cardinality of large sets. Nobody wants to sit there and count how many elements are in extremely large sets. But in order to come up with a pattern, let's start with some small sets and see if we come up with some type of pattern to see how we can figure this out. So this is an easy set. A has the numbers 7 through 11. So the cardinality of A would be 1, 2, 3, 4, 5. Okay, that's not hard. All right, but here's what I want to look at. I took the last number and I subtracted the first number from it. So I have 11 minus 7 equals 4. All right, let's see what happens when we look at another set. Let's look at set B, which has the numbers 20 through 23. So you can easily count that the cardinality of that set is 4. But now let's do the same thing that we just did, and let's subtract 23 minus 20. And when we do that, we get 3. Okay, so then let's look at set C, which has the numbers 9 through 14 in it. You can count those up pretty quickly and see that that is the cardinality of 6. And again, if we subtract the first number in the element from the last number in the element, you're going to get that that operation there will give you 5. So notice how each one of these, 5 as compared to 6, 3 as compared to 4, 4 as compared to 5. So again, there's all of them, there is a pattern there. It's just one less. So if we want to look at a cardinality of a simple ordered set, now that just means that it's just like counting. They're not skipping numbers, they're just going in order. You can take the last number of the set minus the first number of the set and then add 1 and you'll get your cardinality. So in other words, I can take that last number and subtract the first number and then add 1 and get the cardinality of my set. Now let's look at this example. On this example, we have the numbers 15 through 54. Now, if you wanted to, you could go and count all of those numbers, but I really don't want to. So I'm going to try to apply my formula. So we are going to look at 54 minus 15. So that's the last number minus the first number, and I get 39. And remember what we had to do to get the cardinality of the set? We have to add 1. So actually the cardinality of this set is 40. Okay, now let's look at an even uglier set to try to count the numbers between 4 and 964. So the cardinality of this set, we're going to again do the last number minus the first number, which gives me 960. I'm going to add 1, and that gives me 961. Okay, let's look at an even uglier example. Let's look at set C, which contains all of the numbers from -46 to 372. So I've got positive and negative numbers in here. So now we're going to do this the exact same way. We're going to take the last number in the set minus the first number in the set and then add 1. So 372 minus a -46. Now, if you remember anything, when you have two negatives together, um, so remember what happens when you have two negatives together, they turn into a positive. So that's going to be 372 plus 46, which gives you 418, and then you add 1, and so there's 419. Now, aren't you glad you know this little trick and you don't have to sit there and count 419 on your fingers? So there you go. All right, now let's look at some pattern sets. So these, they skip some numbers, but they have patterns. So let's look at a simple set again. We have 12, 16, 20, and 24. If you take a second and look at that, see if you can come up with a pattern. Okay, so the pattern in this case is that you're skip counting by 4. So these are all multiples of 4 from 12 to 24. Now you can find the cardinality of that set simply by just counting those numbers. There's just 4 of them in there. So that's not hard. But I'd like to see if there's a pattern because you're going to get these ugly homework problems that have these patterns in them. Sure would be nice to know how to do them. So it turns out that we can apply the same rule where you take the last number and subtract the first number. But it turns out that I need to divide each one of those by 4. So I'm going to divide by that multiple from the set. So because those were multiples of 4, I'm going to divide both of those by 4. I get 6 minus 3, which is 3. And then I add 1, and it gets me to 4. Okay, so that's in a simple set. Great. Now let's look at a more complicated set. We have 9, 12, 15, ... then 300, 303, and 306. So you can probably see that these are all of the multiples of 3 from 9 all the way to 306. So let's hope that our little pattern here works because that's a lot of numbers to write down and try to figure out. All right, so we have 306. We're going to divide that by 3 because that was my multiple. I'm going to take the first number, 9, and divide it by 3. And so I get 102 minus 3, which turns out to be 99. And then I add my 1, and I get 100. So there are actually 100 elements in that set. That's the cardinality of that set. Okay. Now, let's talk about the cardinality of a Cartesian product. So earlier we've been talking about the cardinality of sets. Now we're going to apply it to the Cartesian products. So I look at set A, which is the numbers 2 through 13. And I can take 13 minus 2 gives me 11, add 1 to it. So the cardinality of that set is 12. All right, now I want to look at set B. Set B is the letters A through Y. All right, now you can't say Y minus A. That's not going to help you at all. But if you know anything about your alphabet, you know that there are 26 letters in the alphabet. This set contains all of the letters in the alphabet except for Z. So we can actually count those. So we can say 26 minus 1, which that 1 was Z. And I know that that set has 25 in it. Well, if you remember back to the first couple of examples, we have that the cardinality of A crossed with B is equal to the cardinality of A times the cardinality of B. So actually, I can just say that this Cartesian product of A crossed with B will be 12 times 25. That's going to be the cardinality of that cross product. So when we do 12 times 25, we get 300. So that product, cross product, will have 300 elements in it. Aren't you glad you don't have to write them all out? You're welcome. Merry Christmas. Okay, now let's find one last example. This example says that show that the following sets have the same cardinality by placing the elements in a one-to-one correspondence. So I have the sets from the first set is the numbers 1 to 997 in order. And then the second set is the numbers 506 to 1502 in order. Okay, so a one-to-one correspondence just means that every element in each set has a corresponding mate in the second set, and each of those mates are unique. Okay, so in other words, I can match 1 with 506, and those two are going to be buddies. They're going to be matched up all the time. I can match 2 with whatever this number is going to be. I can match 3 with whatever number this is going to be, and so on. Okay, so I want to find these missing numbers, and I'm going to talk about these ends here in a second, but let's get the easier ones out of the way. All right, so we know that 2 should be matched up with the second element of this set. So, oh, yeah, I did give you, let's see, both the cardinality of both sets is 997, and you can use that little pattern that we had earlier. So both sets, the cardinality is 997. Okay, so matching up 2 with 507, 3 is going to be matched up with 508. Now, I want to skip over these ends because they're a little more complicated. I'll come back to them. 996 is going to be matched up with 1501. 997 is matched up with 1502. Now, let's talk about what this n and n plus 1 means. The n is just saying that it is any number in this set, any number. So any of these in between the dot, dot, dots. Now, that number is going to be matched up with n plus 505. So let's try it out. Let's say that n is 4. So if this was number 4, this would be 4 plus 505, which would be 509, which is exactly the next number that comes in the set. So if I wanted to know what the 60th number was, that would be n, and I would just take 60 and match it, add 505, and it would be matched up with 565. Okay, so n plus 1 is going to be, that's going to be the next element after n, should be matched up with this number, adding 1 more to it. So that's going to be n plus 506. Okay, so hopefully that wasn't too bad. I know that those ends can be a little confusing. Actually, I know all of this can be a little confusing, but it's just a way to get you to think in a logical pattern and to think mathematically. In the long run, it will benefit you, I promise. Okay, hopefully this helped you with section 2.4, and that's going to finish us up with set theory.